Communities of Region 3 have been implementing the post-construction requirements since March of 2014. These requirements affect how stormwater is managed on new and redevelopment projects. Today's workshop will provide an overview of the requirements, discuss low-impact development principles for land development projects, and offer submittal do's and don'ts for successful review and approval. So with that, I'd like to turn it over to today's presenter, Valerie Huff. Ms. Huff is a senior civil engineer at Wallace Group with a focus on all things water. She specializes in analysis and design of low-impact development, storm drainage, and flood control systems. Valerie was a member of the Joint Effort Review Team, working with regional board staff to develop guidance for implementation of the post-construction requirements. She was also a member of the San Luis Obispo Countywide Hydromodification Technical Advisory Committee, leading up to the regional board's adoption of the post-construction requirements. She holds a master's degree in water resource engineering from Cal Poly San Luis Obispo. Thank you so much for joining us today, Valerie. I'll hand it over to you.
Thank you, Jeff. And as Jeff described, today I will be talking about the Central Coast Regional Board post-construction requirements, which I will be referring to as the PCRs. First, we will go through where these requirements apply. We'll talk about what types of projects, who needs to comply with these requirements. Then we'll go through a brief overview of what the requirements are. And we'll spend most of our time today on how to comply. We'll talk through some of the common design principles. We'll talk through some challenges and lessons learned over the past 7 years of implementation. And throughout this presentation, I will be referencing some resources that are available to you. And at the end of this presentation, there's a slide with a list of those resources and some web links. So that will be coming at the end. Before we start in on the details of the PCRs, I want to provide a framework for our discussion today. And that framework really is the hierarchy and the relationship between the regional board, the municipalities, and the development community. So the regional board prepared and developed the post-construction requirements. They then delegated the implementation of those requirements to the municipalities, who I will also be referring to as your permitting agency or your permitting authority. Right? This is the municipality, it could be a city or a county, who will be reviewing and approving your watershed plan and your post-construction compliance. Now, the municipalities have developed a technical guide as a tool for project applicants. This technical guide is meant to streamline your process of design, implementation, and compliance. Today, I will be talking about some recent updates to the technical guide, specifically through the Mr. Swent program. It's important to understand that the PCRs themselves have not changed. The technical guide is just guidance. The post-construction requirements are the regulations. That has stayed the same. And now it's up to the development community to design and construct and figure out how to implement these PCRs on our project sites. So where your project is located is one of the first things you need to think about. If you are within what is called an MS4 permit boundary, that's the municipal stormwater permit boundary, within the Central Coast region, then you will be subject to the PCRs. In general, the MS4 permit boundaries follow urbanized areas as developed or as identified through the census. So if you are within city limits, you're almost very likely to be within an MS4 permit boundary. If you are within an urbanized area of the county, also the same. If you are within a more rural area of an unincorporated county, or if you have any likelihood that you may be outside of an MS4 permit boundary, you should definitely confirm that you are in or out. It's also important to understand that there are other types of MS4 permit holders. Probably the one that you will encounter the most through design is Caltrans. So Caltrans is a statewide agency. They have their own MS4 permit that applies statewide. Within their right-of-way, their MS4 permit boundary, they have a separate set of post-construction requirements that they have adopted through their individual stormwater permit. So as an example, I worked on a project that was both within and outside of the Caltrans right-of-way. In that situation, you would be applying the Caltrans post-construction requirements within their MS4 limits, their right-of-way, and then you would be applying that local municipality, the Central Coast PCRs, post-construction requirements within their MS4 permit. So it's important to understand where those limits are. If you are outside of an MS4 permit boundary, you're not totally off the hook. You will have to follow the post-construction requirements of the State Water Board through the SWIP program, and that's the water balance calculator. And in addition, there may be some other local requirements that still apply on top of that. The next question of where is identifying what watershed management zone your project is in. And the watershed management zones were delineated and defined by the regional board while they were developing the post-construction requirements. The watershed management zone mapping is available on the regional board website as both PDF and GIS format. And this is an important thing to identify for your project because the actual requirements for your site will be dependent on which watershed management zone you are within. So who needs to comply with these requirements? Any project within the MS4 permit boundary that creates or replaces more than 2,500 square feet of impervious surface triggers these requirements. That's going to capture the vast majority of development projects. Now, there are some exemptions in the PCRs, and this is an important section that you should familiarize yourself with. The most common exemptions would be for linear utilities. So if you are replacing or constructing a new sewer or water pipeline in a paved roadway, you are likely exempt. Temporary structures are exempt, where temporary is defined as 6 months or less. And there's also exemptions for maintenance. So if you're doing an asphalt overlay, if you are removing and replacing pavement, so long as you are not changing line and grade, you are likely exempt. If you think you are exempt, review this section of the PCRs, and also throughout the process, you should be coordinating closely with your permitting agency to confirm that they agree with your exemption. So what are the PCRs? This section of our presentation is going to be pretty brief because there have been multiple presentations in the past that go more in depth into what the PCRs are. And there's some links to those recorded presentations at the end of this presentation today. So the PCRs are broken down into 4 tiers, also referred to as performance requirements. And the PCRs also define 2 project types. So the first is one single family home, meaning one home built under one construction permit, one building permit. If you have a multi-family home development, that's the everything else category. So we have one single family home and everything else. Vast majority is going to fall under that everything else category. So let's talk about that first. So tier 1 is if you exceed 2,500 square feet of impervious surface. The performance requirement is site design and runoff reduction. So under this requirement, there is a list of LID facilities, and you have to implement at least one on your project site. For example, a bioswale, a bioretention facility, using some type of pervious concrete or pervious pavement or another pervious material. And the goal, the purpose of this tier is to try to minimize the amount of runoff that you generate on your site. that you would then have to treat or retain in upper tiers. So the overarching goal here is to, again, minimize runoff so that you minimize the structural controls that you need to meet additional requirements. And it is important to understand that all of these requirements are cumulative, so as you go up in tiers, you still have to meet the prior tiers. Tier 2 is water quality treatment. As soon as you exceed 5,000 square feet of net impervious surface, you are required to treat runoff from the 85th percentile storm, and we'll define net impervious on the following slide. Water quality treatment can be achieved through both on-site infiltration or also through a flow-through facility, such as a bioswale, something that treats the runoff before it leaves the project site. Tier 3 is on-site retention, and this is triggered once you exceed 15,000 square feet of impervious surface. Tier 4 is peak flow management, and this would be matching the pre-development peaks for your 2 through 10-year storm. And this is triggered once you exceed 22,500 square feet of impervious. Now looking at that other category of one single family home, the triggers are a little bit higher for impervious surface. So for a single family home, you don't trigger tier 2 until you exceed 15,000 square feet of net. Same thing for retention. Once you exceed 15,000 square feet of net impervious, you trigger retention. Peak flow management is the same for both at 22,500 square feet. So what is net impervious area? The concept of net impervious area and correspondingly a reduced impervious area credit was developed by the regional board as an incentive for redevelopment projects to reduce the amount of impervious surface, meaning that if you had a site that was, say, fully paved, lot line to lot line, if you reduce that impervious surface through your redevelopment, you would then achieve a credit. So how does this work? On the screen is an example of a site where we did just this. So this was a smaller project. It was a city-owned parking lot, and it was really important for the city to maximize the amount of parking spaces on this lot because it's adjacent to an Amtrak train station, and on the other side of the street is also a ball field, and they get a lot of parking during games. So the city needed to maximize parking, but they also wanted to minimize their effort in compliance with the PCRs. So we set out with the goal of using this concept of net impervious area. So through the project, we removed this long building shown here in white, and we also removed some of the existing paving within the right-of-way. This is the existing condition shown on the left. Over on the right-hand side is the fully developed condition, and the majority of new parking spaces were all constructed with pervious concrete, and the walkways were constructed with pervious pavers. What this resulted in was a reduction in impervious area. So rough numbers, the existing impervious surface was 21,000 square feet. The proposed or the now complete condition was 16,000 square feet. So we achieved a credit of 5,000 square feet. That's how much we reduced the impervious area. Our total new and replaced impervious surface was 9,000 square feet, which would have put us under tier 2. Now we apply that credit. And so our effective or our net impervious area is that 9,000 square feet minus the 5,000 square feet credit. We have a net impervious area of 4,000 square feet, which now puts this project under tier 1. Tier 1 is the easiest tier to comply with. It's a fairly minimal stormwater control plan, minimal documentation. And this means that in the long term, the city's effort of maintenance and long-term reporting to the regional board is also minimal. And this is a win for water quality because we did significantly reduce impervious surfaces, and there is more treatment, more retention than there was in the existing condition. So something definitely to consider if you're in a project site that could be under tier 3 and you think you could achieve that net impervious credit, you could then move yourself down to a Tier 1 project. So what is required to submit for PCR compliance? This is an outline of submittals specific for PCRs. Keep in mind, you will be submitting other documents, your construction documents, possibly a drainage report for flood control requirements. One new thing in the technical guide is the technical guide now identifies that you will be first submitting a preliminary stormwater control plan. This would be during your land use submittal or possibly zoning submittal. And the purpose of the preliminary stormwater control plan is to demonstrate that compliance can be achieved on your project site. The level of detail required to do that is going to vary project by project. We're not expecting that the preliminary stormwater control plan would provide details, construction level details for every facility. But you need to show that you have enough room on your project site to comply. And certainly work with your permitting agency to confirm that the amount of information, the level of detail in your preliminary stormwater control plan is adequate. Now, when you're in final engineering and going for your building permit, you will submit a final stormwater control plan. The final stormwater control plan needs to include detailed calculations for every stormwater facility on your project site. And most importantly, it needs to correspond to your construction documents. So any detail that you show within your stormwater control plan, the surface area of a bioretention facility, the invert of your underdrain, the total depth of your aggregate or your bioretention media. Any of those details need to correspond to what's shown on your construction documents. This is a package that should all be coherent. When you're preparing your final stormwater control plan, you will also submit a draft operations and maintenance plan. Now, during construction, the engineer of record is required to inspect the stormwater control measures as they are being constructed to ensure that they're constructed per plan. And this is an important inspection because one of your subsequent submittals will be a certification that this inspection occurs. Following construction is when you will prepare your final operations and maintenance plan. And this O&M plan needs to be based on record drawings. So if any changes were made to your facilities, that needs to be documented first in your record drawings and then referenced in your final O&M plan. At that time, you will also prepare a maintenance agreement. This is a legal agreement that's recorded with the county. And this agreement means that the operations and maintenance for your facilities are going to be tied to the deed of your parcel and will continue in perpetuity. So let's talk a little bit more about the O&M plan and the maintenance agreement, because this is definitely an area where the permitting agencies are seeing some discrepancies of what's required versus what is submitted. So first off is that certification of construction by the engineer of record, and that's the inspection during construction that I had talked about. Your final O&M plan, again, is based on your record drawings. And the PCRs identify 3 minimum components that your O&M plan needs to include. First off is your O&M procedures. What, when, and how are you going to maintain your stormwater measures? And you also need to include the anticipated cost, the annual cost for this O&M. And you need to include a site plan. Now, the final O&M plan is going to be an attachment to your maintenance agreement. Remember, that's your legal agreement. And that full package, your maintenance agreement and your final O&M plan, is going to be recorded with your county assessor. So the county assessor has specific requirements of documents that need to be recorded. They need to be able to be duplicated with a common printer, and they need to be black and white. So in general, you want all of your pages to be 8.5 by 11. Think ahead when you're preparing your exhibits for your stormwater control plan or your site plan. If you can have everything 8.5 by 11, check with your county assessor. They may allow 11 by 17 or 8.5 by 14, but really try to target that 8.5 by 11. If you can do that ahead of time, it's going to save you some time and effort at the end of trying to transfer everything down to smaller pages. Everything needs to be legible at an 8.5 by 11 size. If you take your 24 by 36 construction documents and shrink them down to 8.5 by 11, they will not be legible and they will not be accepted by the county recorder. After you've gone through all of this, remember that the operations and maintenance will continue in perpetuity. And the project owner will need to demonstrate that by submitting an annual certification of maintenance to the permitting agency. So now we're going to talk about how to comply with the PCRs. This is where we'll spend the bulk of our time today, and this is also where we'll be answering some questions that have already been submitted by attendees of today's training. So thank you to those who submitted questions in advance. And again, we will be reserving a good chunk of time at the end for Q&A. So the most important thing you can do for a successful submittal is to follow the technical guide. So thinking back to our hierarchy, the technical guide was developed by the municipalities as a tool for project applicants. The technical guide is intended to streamline your process of design and submittal, and it also helps to streamline the plan check process on the municipality side. So when you're following the technical guide, when you're using the templates, they know what to expect when they're doing a plan review. And this is going to save you time and money in the long run. Now, I have to stop and give some kudos to Santa Barbara County. So today, specifically, I'm talking about edits to the technical guide for the Mr. Swimp group. But the technical guide was originally developed by Santa Barbara County. So this is very similar to what you will see used in Santa Barbara County, and I know that also some municipalities in San Luis Obispo County use this as well. So Kathleen Garnand successfully obtained some grant funding and put together this technical guide a number of years ago with the intention of it being used region-wide, and that's what we're doing now. But keep in mind that the specific changes I'm talking about today apply to the Mr. Swimp group. So the Stormwater Technical Guide is comprised of multiple documents, and all of these are available on the Mr. Swimp website. So the technical guide is just that. It's a guide, it's a how-to manual for how to comply. Along with that is a stormwater control plan template. And the template really includes every single section that you need to fill out for a successful submittal. One of the new changes to the stormwater control plan template is that we've also included a lot of guidance within that template. So as an example, the screenshot over on the right shows black and red text. The black text are the sections that you need to fill out. The red text is direction for you on how to fill them out and what to include. So through this process, again, it's meant to streamline your effort and streamline the effort on the plan check side. One of the other important things that comes along with the guide is a stormwater calculator. So the calculator is an Excel-based spreadsheet, and it will prepare all the calculations you need for Tier 2, that's on-site treatment, and Tier 3, on-site retention. The calculator is based on a bioretention facility. It was designed and developed to calculate volumes for bioretention. It can be used for other types of features, but you may need to adjust or tweak those results a little bit. And if you are designing a flow-through facility, such as a bioswale, you will need to use some other type of calculation or program. This calculator is based on on-site retention. A couple important things to note is that the calculator does require that you input your project areas by surface type, meaning is it an impervious surface, is it a landscape surface? And so when you're first identifying your drainage areas, you want to try to delineate those by surface type so that you have that ready when you go back to use this calculator. The other thing to think about up front is that the calculator requires you to input values, input surfaces, describe them as either new or replaced. And this is important because if you have a replaced surface, the requirements are slightly different than if you have a new, brand new impervious surface. And again, there have been previous workshops that go into detail on how to use this calculator, and so I'm not doing that today. And there is also a guidance manual on how to use the calculator that's available on Mr. Swen's website. So why is it important to identify surfaces as new or replaced? Well, the PCRs include an adjustment factor for replaced impervious surfaces. And this was meant to help redevelopment projects, knowing that it will likely be more challenging to comply with on-site retention on a redevelopment site, particularly if you're in a built-out area. So that adjustment factor applies for PR3 on-site retention only. And what it is you take your sum of your replaced impervious surfaces and you multiply those by 0.5. You're cutting it down to 1/2. And that results in 1/2 of the volume that you need to retain for the runoff from those replaced impervious surfaces. And the calculator automatically applies that 0.5 multiplier when you designate a surface as replaced. That's important to understand. You want to put in the full area of your replaced impervious surface. The calculator will apply the 0.5 multiplier for you. One concept of delineating your drainage management areas that is really important to understand is that you may end up with DMAs that are different for your different performance requirements. So your performance requirement for treatment, for retention, and peak flow will likely or may likely have very different DMAs. And here's an example of that. What you're seeing on the screen is a roadway widening project. Over on the left-hand side are the DMAs for retention. These are the new and replaced impervious surfaces, where the replaced surfaces are shown in pink and the new impervious is shown in red. Now the PCRs have a clause, and that clause says that if you cannot separate the runoff from existing impervious surfaces and your new and replaced impervious surfaces, you are now on the hook to treat everything for PR2. So what this means for a roadway widening project is that generally you have to you have to treat runoff from your entire roadway section. So over on the right-hand side are the corresponding DMAs for this same project, where everything in green is existing impervious surface to remain. All of that runoff drains directly to our new and replaced impervious surfaces, and therefore we have to treat everything. So this particular clause of the PCRs affects roadway widening projects pretty significantly. I'm not clear if that was the intent, but that is the result, and it's something to keep in mind when you are starting in on a roadway project. And it's also just requires some creative thinking in terms of how you're going to fit in facilities that can treat now both the existing and new impervious surfaces. One thing I did not mention on that prior slide is that your DMAs for peak flow control likely again will be different. In particular, this project has some larger tributary areas draining through the project. So when you're comparing your pre and post development peak flows, you may need to extend outside of your own individual project limits. Another consideration is how you are going to comply with flood control requirements. And this could be the peak flow management of matching 2 through 10 of the PCRs, or you could have flood control requirements from your permitting agency in addition to the PCRs that apply on your project site. If you can use your LID facilities for flood control, it is going to help you comply. So what you're seeing on the screen is an example of a commercial project, and everything that's shown in the colored DMAs is all new impervious surface. So generally with commercial industrial projects, you have a lot of lot coverage. And what you're seeing in green are the areas that we had available for LID. So each of these green areas were relatively shallow LID basins. It can be a real challenge to meet flood control requirements with shallow, smaller, separate basins. And so what we did for this particular project is we connected all of these basins with a storm drain system, so now they act in series. And it works well because this site is relatively flat. So everything drains through this basin here, and for flood control purposes, the flow is metered out through this basin. And water can then back up through these storm drain systems and start to fill out these upstream basins. We were also able to take credit for the volume available in those 18-inch storm drain pipes. It's not huge, but it's something. And together, between these discrete basins and our storm drain system, we were able to meet our peak flow management requirements using just our LID facilities. Now, I'm going to start talking about some specific design features for post-construction compliance. And bioretention is, in general, one of the most commonly used features for compliance. It is what the technical guide will direct you to as a first measure if you need a structural stormwater control measure. And it's also what the calculator is based on. And part of the reason is that bioretention is really reliable. So in general, bioretention provides treatment through the bioretention media, and then it provides retention in usually some type of gravel layer below that. So there are a lot of bioretention details available online through various resources. This just happens to be the schematic detail that's in the technical guide. So this is your bioretention soil mix here, and this is your aggregate layer here with an underdrain. One really important thing to understand, this is in the technical guide, is that you should not be specifying or placing a filter fabric between your bioretention soil media and the aggregate below. So this is definitely a lesson learned over time. Years ago in Bay Area and Southern California, when bioretention facilities really started being constructed, some older details called for that filter fabric. And what we have found is that that filter fabric clogs up over time, and it prevents that water from then getting down into that gravel layer. It's much better to allow those fines to continue on through and settle, have a small layer of fines at the very base of your gravel than it is to prevent that water from getting into your gravel in the first place. So no filter fabric, no separation. If filter fabric is placed in your bioretention, you will have to go back after construction and remove that, and we've seen that happen on the Central Coast. Another item to consider is that you can utilize through your underdrain. So this is your overflow inlet here, and your underdrain pipe, which is typically a 4-inch perforated pipe. You can utilize orifice control. This means that you're not allowing water that would get into your underdrain to flow freely. Rather, you are constricting that outlet, and so the water is allowed to then back up in your bioretention facility. And what that does is it gives you more credit for the available volume within your bioretention. You are able to account for that volume that's within your soil media and maybe even some of the ponding on top of that. Whereas without an orifice, when you're talking about retention, you're only accounting for the volume that's within your gravel. So using orifice control on bioretention can reduce the required size of your facility. What's shown in this schematic, and what I would recommend if you are using orifice control, is a really simple design. Readily available materials, easy to construct. What it is it's a threaded cap on the end of your PVC with a hole drilled in it, and that hole is your required orifice size. If you need to go back, or when you need to go back and inspect your facility, or if that orifice becomes clogged, all you have to do is unthread that cap. You could easily construct a new one if you needed to. So I would recommend following this design where possible. And the calculator will tell you there's an option, a drop-down option, where you can say, yes, I have an orifice. And the Excel calculator will tell you what that orifice size should be, and it will also account for that when it gives you your required volume for compliance. Here is an example of a different type of orifice control. I don't particularly recommend this detail for bioretention design, but I'm using it specifically just to show this type of orifice. And this is a standpipe orifice. So in the previous example, we had that threaded pipe right down here at the elevation of the underdrain. In this example, water actually needs to fill up your bioretention media before it can outflow here through your outlet. This is a clean out that's closed. And so this achieves the same result as the threaded cap with the orifice hole, but there is a caveat. The only way that water can outlet is through this outlet. So anything below the height of that outlet will need to drain through your bioretention media, through your gravel layer. This design is better suited for a soil where you have a lot of confidence in your infiltration, where you have a lot of confidence that that water will be draining. Because if your water, if that stored runoff is draining slower than expected, you can have some longer duration ponding through your media, through your gravel. Another important thing to look at here with this particular detail is, what is our effective area for bioretention? When I'm calculating how much infiltration I am achieving, what can I account for? And you can account for the area that is flat, that fills up like a bathtub. So when you're checking that you've met your 4% minimum surface area, if you're hand calculating or doing infiltration calcs in a separate program, you use the flat area of your bioretention. You do not include the slope. This particular detail shows native soil coming down the slope and then transitioning into bioretention soil media. In many cases, you may have concentrated flow coming down your slope face, and then you would certainly want some rock or cobble here to protect from erosion. In general, the bioretention media is going to be much looser. By design, it's a much looser material likely than your native soil. I would recommend that you extend your native soil down this slope face to avoid any potential for erosion here. Now you can, if you need to, if you want to achieve a greater storage volume, you can certainly extend your gravel layer beyond that. But it's a cost balance consideration of now your overall excavation would need to be bigger to achieve that. So I'm going to move on and talk about pervious concrete and pervious pavers. Again, a relatively brief discussion. We have a reference for you at the end of this presentation for another workshop that went into detail about pervious concrete. So pervious concrete is a great way, or pavers, is a great way to minimize or reduce your impervious surface on your project site. These materials, though, are highly dependent on the quality of construction. If you are speccing and designing pervious concrete and pervious pavers, you need to have a really solid set of plans and set of specs to go along with that to ensure that your contractor is going to have experience in placing these materials. What's included in the technical guide is really just the tip of the iceberg. You, as a project designer, are going to need to spend some time to get this right. And get it right, I mean, get the construction side right. This project happens to be the project I used as an example for net impervious area, the parking lot redevelopment project. So all the stalls here were pervious concrete and the walkways were pervious pavers. So one challenge with pavers and concrete is that in general, our sites are never perfectly flat. If your site is perfectly flat and filled up like a bathtub, you could account for all of that retention volume in your aggregate below your pavers or concrete. Generally, that is not the case. We are going to have some type of slope, and you need to account for this in terms of how much water you can store below those pavers. So the graphic over on the far right shows a couple options for doing this. You can extend the depth of your base to account for that slope and achieve more retention. If you have a highly sloping site, you could even consider just capturing everything on the downhill side of your pervious concrete if that works for your retention volume. Another thing to keep in mind is that you may need to include some subsurface check dams. Maybe these are highly compacted native soils. Maybe it's concrete. But you need to ensure the stability of that subgrade as you're storing water below your pervious concrete. There are really two types of pavers that would be used on a project site. The type of paver that's shown here on the screen relies on space between the pavers to allow for infiltration. So the pavers themselves are impervious and there's a gap. And if you look closely on the left, you'll see the little rounded bump out on the paver, and each paver has those and they match together to get the spacing in between. That spacing is really critical because ADA requirements dictate the maximum allowable spacing for pavers to be an ADA compliant surface. If your contractor places these pavers such that that spacing is exceeded, now your surface is no longer ADA compliant. So this is really important to have a tight spec and to check in the field. When you're working with pavers, you generally have some more resources available from the manufacturer. So make sure to get all of the manufacturer's recommended specs for both design and construction. Now these pavers again rely on the rock and the area between the pavers to allow for infiltration. And here's an example of what that rock might look like immediately following construction. So it is a challenge to get that aggregate placed into the linear voids between those pavers. And you need to anticipate that there's going to be some maintenance work immediately following construction. You are going to have to clean up that rock following construction and throughout the life of the project. So these types of pavers may need rock to be replaced over time. If that rock was clogged with, say, sediment, if you had a flood flow that came over and placed mud in those areas, you may have to even go back and vacuum it all out and replace that rock. So this particular material is not a set it and forget it material. Another consideration with pavers are what are often referred to as pervious pavers. And these pavers are constructed of pervious material. So it's like a unit block of pervious concrete. This type of paver really minimizes the potential for the construction side of your project to result in issues. So these are a little more foolproof, and these are shown right around the tree wells here. These are all pervious pavers. So there's no gap between the pavers because, again, the material itself is pervious. And so what you are constructing is a contiguous surface of pervious pavement using a unit block. These are generally a little more expensive up front, but they will very likely minimize your O&M costs in the duration. And they also minimize the chance that something is going to happen during construction. So this is our first question that came through from one of our attendees today. And the question is, what surfaces are considered pervious or impervious for threshold calculations? So keep in mind the tier that your project is in is dependent on your amount of impervious surface. So understanding up front what is classified as what is really important so that you correctly identify your tier. So for this, I pulled up the definition of impervious surface directly from the PCRs. So the PCRs have an attachment that's all definitions. This is actually just a short portion of the impervious surface definition. And that is a hard, non-vegetated surface that prevents or significantly limits the entry of water into the soil mantle, as would occur under natural conditions prior to development. So, certainly a lot of room for interpretation here. The takeaway for this is it going to significantly change conditions from pre-development to post-development? And if you have any question on what is considered pervious or impervious, again, please work closely with your permitting agency. The permitting agency is the final authority in terms of approving your stormwater control plan. So here are a couple examples. This question specifically asked, what about a rural driveway? Rural driveway meaning if I place rock to stabilize my driveway. So the picture on the left is what I would consider a typical rural driveway. Likely there wasn't a whole lot of modifications to the subgrade, to the native soil, maybe slightly compacted, and then rock was placed on top. In this case, the rock is helping to stabilize the soil. It's helping to hopefully minimize erosion. It may even be allowing for a little bit more water to pond through that area. I would definitely consider this to be a pervious surface. And in general, that's what I've seen through submittals, is that if you have a parking lot, a driveway, some section of a rural road that's just rock, it can be considered pervious. On the right-hand side is DG. So decomposed granite is also rock. It's often highly compacted. This particular picture shows a DG parking lot that was constructed with a stabilizer. A stabilizer will generally hold that DG together, and it also fills in the void so that you don't have as much room, you don't have as much capability for that surface to infiltrate. So the picture on the right, I would describe as impervious. It certainly limits the amount of water that could infiltrate the soil, and especially if you had a sandy soil to begin with, it would be a significant change from existing conditions. So the next topic that we're going to get into is infiltration testing, and there were a number of questions that came in regarding this. We're actually going to take a quick break before we dive into this, but one thing that I wanted to point out in particular regarding this question of pervious versus impervious. Think back to the hierarchy of the regional board developed these PCRs. They delegated that implementation to the municipalities, to your permitting agency. And now it's the design community that works with those to design, construct our projects. Now, the permitting agency is going to approve your stormwater control plan. They are going to be very carefully plan checking things such as what is considered pervious and impervious, right? What are the details that you provided for your pervious concrete? How are you going to ensure that this pervious concrete is going to perform? And they are going to that level of detail because if the regional board chose to come and audit their compliance with the PCRs, if your project or a project was found to be out of compliance and had been approved by your permitting agency, that's now a compliance issue for your permitting agency. So your permitting agency can receive an NOV, a notice of violation, if they approve the project that is then found to be out of compliance. So if you submit a stormwater control plan and you get a long laundry list of comments related to things like this, what is pervious, what is impervious, you need to add more detail to your bioretention, whatever it may be, and I understand that it's a challenge to comply with these requirements. The permitting agency is really needing to follow the letter of the law because of that potential for an audit for an NOV. So keep that in mind, right? As you are preparing your stormwater control plan, the PCRs are the regulation. The technical guide helps to get you there. And at the end of the day, it's the permitting agency that's going to be on the hook for that implementation, for that compliance. All right, so we are going to talk for a while today on infiltration. So infiltration is really, I'll say, a cornerstone of, of design when you have to account for on-site retention. And I have seen a lot of questions. I have had a lot of questions over the years of implementation. And, you know, one thing to note in general regarding the technical guide, regarding the PCRs, is that guidance is evolving as we learn more, right? As we construct and place these types of facilities in the ground and observe their performance, we have lessons learned. We have lessons learned through construction. And so a lot of the updates that are coming through the technical guide are based on those lessons learned over the past few years. And certainly we've learned some things about infiltration also. So the question here is really multiple parts, is can you provide some guidance on testing for a surface stormwater control measure, or SDM, as compared to a subsurface stormwater control measure? How do we interpret the test results that we receive from a geotech? What are some factors of safety that we should be considering? How do we manage multiple infiltration rates that were tested on the same site? And are there resources available for when on-site testing is not performed? So first off, I want to talk about the difference between percolation and infiltration because it's important to understand. So infiltration is the movement of water into the soil. If you have a puddle of water on the ground, it is infiltrating into that soil surface. Percolation is the movement of water through the soil profile. So percolation can occur both horizontally and vertically in all directions once that water is now into the soil profile. The most common type of test that's done in our region is a percolation test. And Earth System Specific did a good job of putting together some guidance on infiltration testing. And it looks something like what's shown here on the screen. This isn't exactly it, but it's close enough for discussion. So when Earth Systems started out in developing this guidance, their goal was to come up with a testing method that could be done utilizing standard equipment that they would generally have for a typical geotechnical study, on-site study, and also something that wasn't going to take a whole lot of additional time. And what they came up with was a recommendation for a percolation style test. And what this is it's a geotechnical boring, and these borings would be conducted across the project site. And a few of those borings would be selected for testing. And the testing would be to place a perforated pipe into that boring, fill that annular space with gravel, now add water until you saturate the soils. And once your soils are saturated, you monitor how quickly that water is dropping, right? What is the rate of drop in that hole? This is a percolation test in that you are subgrade, you're within the soil profile, and you also have water moving in all directions. You have water moving horizontally, you have water moving vertically. Compare that to a typical bioretention. Certainly in our area where we're relying on this gravel bed, this subgrade storage, this is more of a percolation type condition. You're already in that soil profile. However, your typical bioretention facility has much more horizontal area than it does actually vertical sidewalls. So let's take a look at an example of this. So a typical diameter for a borehole would be 6 inches. And let's say we have 3 feet of standing water in that borehole as your geotech is testing those infiltration rates. You have a sidewall to base ratio of 24, meaning the area available for percolation around the exterior of your borehole is 24 times the area along that 6-inch diameter base. Now, Earth System Specific defined a small-scale stormwater control measure in their guidance. They state that their guidance is intended for use in a small-scale SCM, meaning that an SCM where the sidewall percolation provides a significant component of percolation relative to the bottom of the SCM. So they recognize that this guidance really provides a testing method that would correspond to something like an infiltration trench, something linear in nature, something that relies on underground, likely underground storage through gravel, something that has a lot of sidewall area. Compare that to a typical bioretention. And I selected a small facility for comparison. If you had a bioretention facility that was 4 feet wide by 6 feet long and 2 feet of gravel, you now have a sidewall to base ratio of less than 2, meaning that your sidewall area is less than 2 times your horizontal surface. This is much different than the tested condition where we're looking at 24. Right? And a bioretention facility would typically be even wider and longer than this, meaning that sidewall ratio would come down. It's not uncommon that your tested water depth in your borehole would be 4, 5, maybe even 6 feet. And then that sidewall base ratio comes up, increasing that discrepancy. Now, the other thing about this type of test is that you are provided results in inches per hour. That inches per hour is based on all of that surface area available for percolation. If you had a borehole filled 3 feet with water, you would expect less percolation than if you had a borehole, say, filled 6 feet with water. in both conditions, you are still provided the same result in terms of inches per hour. So even in the same borehole, in the exact same location, on the same day, you could have different results depending upon how much water you had in that borehole. So what do we do? All is not lost. This is still a completely valid method of testing, but we need to account for this sidewall area through what's called the Porcher method. So the Porcher method is described in multiple resources. I think the best one that does it is the Riverside County Manual, and there's a reference to that at the end of this presentation. It's also cited in a number of other manuals. The City of Santa Barbara Manual cites it, the San Diego County Manual cites it, the Orange County Manual cites it. What the Porcher method does is it accounts for all of your surface area available for percolation. It might look like fancy math. At the end of the day, it's just taking into account the height of your standing water, the surface area of your borehole, and basically resulting in what you could consider a unit infiltration rate. And that is the design infiltration rate that you would then apply to your bioretention design. So if you're using a computer program, if you're using the Excel calculator, that calculator is assuming that that infiltration rate occurs over this full surface of your bioretention facility. If you apply directly your results from a percolation type test, you would be vastly overestimating what could occur here because of that area, percolation area available in a percolation type test. So this is a very important step. It can result in a significant reduction in a design infiltration rate compared to what's tested. I mean, on the order of magnitude of 10 or more. 10, I've seen 20, I've seen 30 times reduction in what is an appropriate design infiltration rate compared to a percolation type test. Now, an alternative method of testing is a double ring infiltrometer. So the reason why Earth Systems steered away from the double ring infiltrometer is because it takes special equipment and it takes more time. So all of this is not to say that the percolation testing is not appropriate or not preferred. Certainly it meets the goal of using standard equipment, minimizing time and cost. But you, as the designer, need to understand what you're working with. Now, looking at this example on the screen of a double ring infiltrometer, what this does is it tests surface infiltration rates. The outer ring remains saturated, and what that does is it limits the movement of water from that inner ring to strictly just the vertical direction. So the double ring infiltrometer is really good at estimating surface infiltration rates for facilities that do not have a lot of sidewall percolation. An example would be any standard detention basin. Once you have a large basin with a shallow depth of ponding, and keep in mind that for these water quality storms, the 85th and 95th percentile storms, we're talking about really shallow ponding. Your sidewall component is basically negligible. Now, looking at the picture on the right, this is an infiltration swale. So there is no subsurface storage in this facility. If you are designing a facility that relies on surface infiltration, it is my opinion that you will get a much better approximation of what you will actually achieve on site through something such as the double ring infiltrometer. So there's a lot of interaction right in that top layer of soil between the vegetation, the soil, the chemistry, the biology. It's certainly all more than I understand. But the roots of that vegetation, especially in hard compacted soils, provide really good pathways for infiltration. And you will see a significant difference in surface infiltration between a heavily vegetated facility and a facility that's, say, just newly ripped earth. So again, my opinion, it may very well behoove you to take the time and make the effort to actually do a double ring infiltrometer test if you are planning on counting on surface infiltration through a vegetated facility. Your results may be better, meaning you may achieve higher infiltration rates than what you would see by doing a percolation type test. Now, one of the questions was, what do I do if I don't have on-site testing? So again, let's thank Santa Barbara County. So Santa Barbara County was working with a consultant, Dan Cloak, who is an engineer up in the Bay Area. In the Bay Area, they have been constructing bioretention facilities much longer than we have here on the Central Coast. And Dan Cloak really wanted to answer this question because he understood that it was a burden to have to test infiltration rates, right? There's uncertainty in terms of varying soil profiles, in terms of how the test was conducted, in terms of applying safety factors, right? There's a lot of question and potential uncertainty, room for error when it comes to on-site infiltration testing. And he saw that burden and he wanted to try to minimize that. And through his work, Dan Cloak and a group of other engineers had studied constructed bioretention facilities in various soil conditions. So they were measuring rainfall rates, they were measuring rainfall depths, they were measuring the amount of water that was coming through these facilities on the outlet side. And through that study, my understanding is how they developed these recommended infiltration rates that are built within the calculator. These infiltration rates are dependent on your hydrologic soil group as defined by NRCS. So within the calculator, if you choose a hydrologic soil group A or B, the calculator will assign an infiltration rate of 0.75 inches per hour. If you choose an infiltration rate of C or D, the calculator will assign 0.25 inches per hour. Specifically, that 0.25 inches per hour for a hard clay soil is likely more than you would see if you were doing a percolation type testing. And really this is because this is based on a field observation of a heavily vegetated facility, a bioretention facility constructed and in good condition. And so this standard rate of 0.25 inches per hour is giving you that benefit of the interaction between the soil and the vegetation, right? Instead of having to go out and do your double ring infiltrometer to see that, hey, yeah, I actually get more infiltration than I think I may, this rate it is reasonable, it's field tested, and it accounts for that benefit of being heavily vegetated. In the absence of on-site data, or if you feel like this value is more appropriate than your tested on-site data because you will have vegetated facilities, these values are standard in the calculator and you can certainly use them. So let's talk about safety factors. The calculator has two built-in safety factors. The first safety factor is for a bioretention facility. And that safety factor is 1, meaning there is no safety factor. So why is that? Well, 2 reasons. The standard rate, infiltration rate for design, the 0.25 and 0.75 inches per hour, is based on the ground observation. Constructed facilities, right, we've already removed a lot of the unknowns. Second is that bioretention is required to have long-term operations and maintenance that maintain that infiltration rate over time. So by design, a bioretention facility has a layer of mulch that is intended to capture fines, debris, vegetation, trash. And that mulch should be removed and replaced. So by replacing that mulch, maintaining your surface infiltration, maintaining really the functionality of your bioretention system, you are given this credit, meaning you do not need to apply additional safety factors if you're using bioretention. Now, if you choose what's called in the calculator as direct infiltration, now you have a safety factor of 2. And this would be any other type of facility that doesn't have that built-in functionality of removing all those fines and debris that could otherwise decrease your infiltration over time. Now, safety factors are based on engineering judgment. So this is, again, one of those things where if you are following the technical guide, if you are using bioretention, I think it's certainly appropriate to use these types of safety factors. If you have a site with more variable conditions, if you're using on-site testing, if you have a large site and you've only tested a couple locations, if you have a lot of variability in your soil profile, these are all reasons why you as a designer may want to select a higher or a different safety factor. There are manuals available that go into detail, like high levels of detail of selecting a safety factor based on the size of your site, the type of your testing, how many tests you performed, and those are again referenced at the end of this presentation. So that wraps up the discussion on infiltration. And now we're going to move on and start talking about some technical infeasibility. So one of the questions that came in is, my site has high groundwater, less than 10 feet. My site also has very poor infiltration. How can I achieve PR3? So the PCRs has what's referred to as technical infeasibility, which identifies a number of various conditions on your site through which on-site infiltration may not be feasible. Both high groundwater and poor infiltration are on this list. So if you indeed had both of these conditions, I would say this meets the criteria for technical infeasibility. Again, make sure to confirm with your permitting agency that they agree that your site meets this infeasibility criteria before you go down the path of complying in this manner. So I have confirmed that my site does indeed fall under that category of technical infeasibility. What does that mean? Well, what that means is you still have to meet, let's say you're a Tier 4 project, you still have to meet Tiers 1, site design, 2, treatment, and 4, peak flow control as stated in the PCRs. You now have a different path of compliance for PR3, on-site retention. So rather than calculating your runoff volume and designing your SDMs for that volume, now what you need to do is dedicate 10% of your site to what is called the equivalent impervious surface area, also defined in the PCRs. So the EISA, the equivalent impervious surface area, is the sum of all your standard impervious surfaces, roofs, concrete, asphalt, and also some pervious surfaces multiplied by a factor. Those factors are shown in Table 1. So as an example, if you had a commercial site that was primarily impervious surface and you had some grass, some managed turf along your landscaping perimeter, then your equivalent impervious surface area is all of those impervious surfaces plus your turf multiplied by the factor shown in the table that's dependent on soil type. Now, you calculate your EISA, you take 10% of that, and now that resulting surface area, that 10%, needs to be dedicated to what the PCRs call retention-based stormwater control measures. There's no clear definition of how much volume you would need to store in those SDMs or what the design criteria is. It just needs to be retention-based. So you could have some native landscaping, or you could have some more traditional landscaping with trees and shrubs that allows for some ponding of water before it drains to a storm drain. That would be retention-based. right? You could have a bioretention facility. Now you don't have a defined volume, but you need to provide a retention-based surface. You could have a heavily vegetated bioswale. That's going to promote retention. Any one of those features can be used to meet this criteria. They just have to add up to that 10% of your EISA. So the question now is, what happens when that 10% EISA cannot be achieved? Well, now you move into what's called alternative compliance. So the PCRs has a section dedicated to alternative compliance. One option would be off-site compliance, meaning that somewhere in the same watershed as your project, you are going to now retain the equivalent volume that you cannot retain on your project site. Two other options would be a watershed or a regional plan. This is a large-scale plan that looks at a larger geographic area to demonstrate or to identify how you could meet the PCRs, the equivalent of the PCRs, in larger scale facilities as opposed to individual project sites. This type of plan would need to be prepared in advance of your project by your permitting agency and approved by the regional board. Similarly, your permitting agency could have identified what's referred to as an urban sustainability or USA. A USA is a high density area, such as a downtown, where your permitting agency has identified that implementing the PCRs on site is going to constrain the type of dense development that is zoned or designated for those locations. So within an urban sustainability area, PR3, the on-site retention, is scaled back to give the site designer more flexibility for a higher density site. Again, that USA would have to be prepared by your permitting agency and approved by the regional board and in place at the time that your project is being developed. So all of these things are to say that once you start going down the path of off-site compliance, now you're increasing complexity, you're increasing costs, right? If you can achieve the PCRs on site, that's going to be your best bet for a more streamlined submittal, lower compliance complexity, hopefully lower costs. So this question continues, okay, what happens when my 10% EISA and my off-site compliance cannot be achieved? Run for the hills, right? There might be a very small number of projects to which this applies. The PCRs have an off-ramp. It's described as other situations as approved by the Central Coast Water Board Executive Officer. This is a case where the project applicant would be working directly with the regional board to try to identify an alternate means of compliance. This to me says long timeline, much more complexity, much more cost. If you find yourself in this situation, my recommendation is to do whatever you can to meet that 10% EISA. It's a challenge for dense sites, especially any type of commercial or industrial site. But if you can achieve that, maybe you can replace some of your impervious surfaces with pervious concrete. Maybe you can add a little bit more landscaping area within your parking lot. Whatever you can do to try to meet that 10% EISA and be within the bounds of the PCRs is going to definitely reduce complexity, timeline, and cost compared to this other route of trying to come up with an alternate compliance through the regional board. One really important aspect I want to bring up of technical infeasibility is construction near and adjacent to slopes. So this is a project site that we were recently working on, and this is an area for a roadway widening project. So the existing pavement that you see, this is the existing condition, was widened in both directions, meaning that edge of pavement was getting even closer to the slope face. So during our preliminary site review, we're walking along the roadway and noticing all along the slope face are ground swirls and ground swirl holes. In our project experience, we have seen significant erosion and slope failure because of ponded water piping, finding its way through a ground swirl hole and coming out the slope face and basically eroding everything back up. It doesn't take a lot of water for this to happen. Your water could be surface, meaning a small puddle. It could be subsurface, meaning you're storing it underground and it's finding its way through these holes. Even in the absence of any kind of burrowing rodents, you can expect that water is going to try to find its way through this slope face if you're storing it below ground. So the point being is that if you are anywhere near a slope, I mean, even within a couple hundred feet of a steep slope, you need to be working very closely with your geotechnical engineer, and this is very likely a case for technical infeasibility. We claimed technical infeasibility for this particular corridor of the roadway widening project everywhere where we were adjacent to the slope face. If you decided to design and construct SCMs, that could be a huge liability in terms of potential erosion or potential issues on that adjacent property. So really take this seriously. Moving on from technical infeasibility, this was the last question that came in. And the question was, can you please talk about Performance Requirement 5? So the PCRs identify Performance Requirement 5 as what's called special circumstances. So there are some cases where your the requirements may be different or scaled back if you fall under one of these categories. So the categories are, first, highly altered channel, second, intermediate flow control, and third, historic lake and wetland. Highly altered channel means that you have a channel that's hardened with concrete lining, some other compacted lining from your project site all the way to an outlet of a large water body. And those water bodies are defined in the PCRs, generally a lake or an ocean. So as an example, a lot of Pacific Grove and Monterey may fall under this category because they do indeed discharge to the ocean, and a lot of that is through a storm drain pipe, right? Which could be considered a highly altered channel. Now, this particular case means that you can scale back on your peak flow management. So your on-site retention, your on-site treatment remains the same. You can scale back peak flow management. The thinking is that sending peak flows through these facilities is not going to be damaging or otherwise altering a natural stream. It is up to the project applicant to demonstrate that you can safely do that within the existing facility. So you would have to show that you can safely route your post-development peak flows through these facilities without causing flooding. So you're not off the hook of analyzing peak flows, you just don't necessarily have to control them on your project site. Similarly, for the intermediate flow control, in this case, you would have a large-scale existing retention or detention basin downstream from your project. If you can demonstrate that you can safely send your peak flows to this existing facility, and that facility can manage your peak flows, then again, you can scale back for managing the peak flows on your project. A really important aspect of this is as soon as you are using an off-site facility, such as an existing basin for PCR compliance, that facility is now subject to the same operations and maintenance protocols that any on-site facility would also be subject to. So you will also be responsible for preparing an O&M plan, working with your permitting agency and their existing O&M staff to ensure that this O&M is going to occur for the perpetuity of your project, just in the same way that would happen if you had this facility on your project site. So again, these special circumstances may be appropriate for your project, but they can also increase complexity for compliance if you are now talking about preparing O&M, analyzing, or otherwise managing these large-scale facilities off of your project site. The special circumstance for historic lake and wetlands is just that. If you think that your project site, or know that your project site was at one time a historic lake or wetland, you may be able to reduce the requirements for on-site retention and peak flow management. The idea being that if it's a wetland, you weren't retaining water anyway, and if it was a lake or wetland, that you're not increasing peak flows. This particular circumstance requires that you first delineate the historic lake or wetland. Then you would have to work with the regional board to have that delineation approved, extending your timeline, extending your complexity, possibly extending costs up front, and at the end, then you would not have to comply on site with PR3 or PR4. This is actually the last question that came through. I stand corrected. So let's talk about underground retention. Underground retention is becoming a more common way of complying with the on-site retention requirement, in particular for those projects that are space constrained, commercial, industrial, high-density residential. So the question was, if underground chambers are used to comply with PR3 on-site retention, can they also be used for PR2? And is pretreatment required? So, infiltration on-site is the preferred method of meeting both PR3 and PR2 according to the PCRs. PCRs outline a hierarchy of ways that you can comply. Infiltration is the #1 method. So the answer to that first part is certainly yes. If you are infiltrating water on site, you're meeting the preferred method of compliance with PR2. Now, is pretreatment required? The long-term operations of these facilities is dependent on them, just like any other type of subsurface retention, such as the gravel layer in your bioretention. It's dependent on them maintaining that percolation over time. And so absolutely you need pretreatment, right? You need to capture upstream any sediment, any debris, any trash, anything that's going to be flowing to these facilities that could decrease that long-term percolation. Now, oftentimes pretreatment is highly recommended or even required by the manufacturer. And they may be able to provide you some type of pretreatment unit. Maybe it's a CDS unit. Maybe it's a separate vault that's built into the system. Those types of units are not considered to be low impact development features. According to the PCRs, if you meet PR2 with a facility that is not low impact development, you have to justify the use of that type of facility. You have to show that LID was not feasible to accomplish on your project site. So you can, upstream of these type of facilities, include, let's say, a flow-through bioretention facility, right? Your water quality storm is directed to a bioretention facility with an underdrain that would then go to these to these underground units. That would be an LID treatment that is likely compatible with underground retention. Similarly, you could use a bioswale, something that's going to treat the water quality flow and help to remove some of those fines and sediments upstream of your underground retention. That in the scope of the PCRs would be classified as LID. So you need to show that you have provided a surface LID facility for that pretreatment. Or you need to be able to justify why you cannot feasibly do that on your project site, which is why you've used a CDS unit or other type of facility. If you had, say, a bioswale that was providing that pretreatment, you're very likely going to need the manufacturer recommended treatment in addition to capture trash, to capture vegetation, to capture that larger debris. So make sure to work closely with the manufacturer to confirm you're meeting their criteria, and also understand this nuance of the PCRs require surface LID for treatment. If you can't do that, you need to justify why. And that was the final question. So, as promised, here's a list of resources, a few of my favorite things. First off is the Mr. Swamp website. And so on that website, you'll find the technical guide, all the attachments that come with it. You'll find the calculator, the instructions for the calculator. And the Mr. Swamp website also has references to all the infiltration guidance that I had discussed today. The Santa Barbara County website does a really good job of outlining O&M plans and also some sample O&M agreements. Again, it's up to you to work with your permitting agency to use an O&M agreement that's compatible with their clerk recorder, with their process. The Santa Barbara County website also has pre-recorded PCR workshops. There is a series of workshops that were hosted by Santa Barbara County that go into much more detail on the basics of the PCRs, how to use the calculator, how to use the technical guide. All of that is recorded. Another really great resource is the Central Coast LIDI, Low Impact Development Initiative. And there's a number of different resources for both design and construction guidance, such as standard details, standard specs, plant lists. There's also a library of different training videos available. My favorite guideline for pervious pavement is Caltrans. They go into a really high level of detail of the different design considerations and criteria that you need to include on your plans and specs. Similarly, I think that for flow-through treatments, such as a bioswale, the Caltrans design guidance is the most complete. I would recommend going there for any vegetated flow-through facility. And then last of all, but not least of all, is the Central Coast Regional Board website. And this is where you'll find the PCRs themselves. And this is where you can download the WMZ mapping in GIS format. I believe the Mr. Swamp website has it in PDF only. So you can get that in a GIS format so that you can better zoom in and out to your project site. And they also have all the identified rainfall depths for the 85th and the 95th percentile storm. So with that, I am going to stop talking for a little while. And I just want to point out that here on this slide is my contact information. I would be more than happy to answer any questions that we don't get to today. We purposely left a good chunk of time for Q&A because we know there's questions. We know the PCRs are complex. They are challenging. And certainly there's questions that continuously come up with various types of projects. So if you have a nuance on your project that you want to talk through, if you have some questions that we don't get to today, please feel free to reach out. My phone number's there. Give me a call, and I'm available.
We've gotten a number of questions from folks, so thank you to everyone who's submitting questions. And we'll just start going through them. The first question, is it considered new, replaced impervious area if you don't change the line and grade?
So that question goes back to our discussion on exemptions within the PCRs. If you are not changing line and grade, then that would generally be considered maintenance. You know, there may be some other nuances that definitely read through that section if you're considering that your project may be exempt. But maintaining line and grade in general, yes, that would be an exemption. And the reason being, what the regional board has told me is that in their view, if you are changing line and grade, now you are creating an opportunity for stormwater treatment that may not have been there in the existing condition. And that is really in their mind, the difference between maintenance versus a new or replaced surface.
Great. Okay. The next question we received is, can you talk about how incorporating green roofs can help a project, especially in a redevelopment setting to meet the PCRs?
Sure. So a green roof would be considered a pervious surface. So if you have a redevelopment project, you're likely space constrained. And keep in mind that the amount of impervious surface is going to really dictate what tier you are in. So the green roof does two things, right? You could design it to retain or treat a certain amount of volume as a means of compliance, but it also reduces the amount of impervious surface on your project site. Traditional roof, impervious, green roof, pervious, you may be able, through the use of green roofs, to actually reduce the tier that you have to comply with.
Okay, great. Here's a quick question. Is artificial turf considered an impervious surface?
So that is a really good question. And again, I would go back to how it is constructed. So that concept of, are we significantly changing the conditions from pre-development to post-development? So as an example, I recently watched one of my neighbors have a large area of artificial turf installed. Curious because I have never seen it installed. And what their landscapers did is they placed a large layer of rock between the native soil, the subgrade, and the artificial turf. And they compacted that rock, but it was more of like an aggregate. And then they placed the turf on top. And I would say in that case, if the turf itself allows the water to come through, and you haven't significantly changed the native soil below, that could be considered a pervious surface. I've also seen turf that was placed on top of a highly compacted, stabilized, decomposed granite. And that was one of the examples we looked at. In that condition, you are, for the most part, sealing off that native soil before you place the artificial turf on top. So I would say, confirm that water can flow through that artificial turf. Generally it can. And then it depends upon how you are treating your subgrade and your native soil below.
Okay. What is the difference between retention versus detention basins?
Okay, so retention means that you are retaining, you are holding water on site. Detention means that you are slowing that water down. So a retention basin, you can picture it very simply as a hole in the ground. That water stays there. A detention basin has an outlet. It has a pipe that allows water to slowly leave that facility over time.
Okay. Can a civil engineering firm perform the double ring infiltrometer test, or must it be performed by a geotechnical engineer subconsultant as part of the geotechnical investigation?
That is a really good question, and I don't have the specific answer to that. I suspect that it would be outlined somewhere in the Engineers Act, and certainly it falls under the category of your level of competency, right? The Engineers Act requires us to act and serve within our areas of expertise. So if a civil engineer has some training in how to properly operate that double ring infiltrometer, and they could say self-certify that it was their level of expertise, I would think that would be fine. But I don't know if there is any other legal issues related to that.
Do underground chambers need to meet the 48-hour drawdown requirements?
Thank you for bringing up that 48-hour drawdown. So I did not mention that through the course of my discussion. The 48-hour drawdown is important to understand that the PCRs define that any retention facility needs to fully drain within 48 hours, and that's for the design storm, typically the 95th percentile storm. Otherwise, you need to increase the volume of your facility by a factor of 1.2. And the purpose of that factor is to account for potential back-to-back storms. So if your facility, let's say, takes 72 hours to drain, and after a day and a half you get another storm, you want to have that extra buffer to capture that volume. So any form of retention, whether in bioretention, in an underground chamber, any form of retention, the design engineer needs to calculate how long it will take for that facility to drain. If it's more than 48 hours, then yes, you need to account for that multiplier.
We've received a number of questions regarding pervious versus impervious. One question was how is hard defined? And other folks are really wondering if there's further guidance from the regional board on this issue, just to ensure there's not inconsistency across jurisdictions.
Yeah. That's a really good question, and I am not aware of any further guidance. I think it certainly would be beneficial for our region as a whole to have some more guidance, but I am not aware of any. I have oftentimes looked to other design manuals also, and I can't say that I have an answer of a detailed list of surfaces, but I think that would be helpful. At the end of the day, again, it's also going to be dependent on how you are constructing your facilities, right? For just as an example, I have worked on a project, a large solar facility, where all the roads were going to be native soil, but we were compacting them to 95% compaction. In that case, the county required that we assume some increased amount of runoff from that native soil because of the level of compaction. So, even if we had a complete list, there's always going to be that question of how is it constructed?
We're getting a number of questions about the EISA and the 10%, meeting the 10% goal. Some folks have just asked if you could go over that section again.
Sure.
So maybe just to kind of refresh everyone's about how that works.
Yeah, I'll go ahead and jump back to those slides. Let's see here. So here's the slide where we spent most of the time talking about EISA. And again, EISA is comprised of both your standard impervious surfaces, concrete, asphalt, and roofs, in addition to a select number of pervious surfaces, and those are shown in this table. This table and this text is from Appendix E, or Attachment E, I should say, of the PCRs. And so Attachment E goes through a step-by-step process of how to calculate EISA. And I would highly recommend going through that section of the PCRs if you are pursuing this method of compliance. So let's try to do some easy math. Let's say you have 1,000 square feet of a traditional impervious surface, and you also have 1,000 square feet of managed turf with a type D soil. So to calculate your EISA, you would take your 1,000 square feet of roof concrete paving, whatever that is, And then you would take your 1,000 feet of managed turf and multiply that by 0.25. So if you look over on table 1, for a type D soil, your correction factor is 0.25. So you would have to include 250 square feet of that 1,000 square feet from your managed turf. So in that case, your equivalent impervious surface area would be 1,250 square feet. You multiply that by 10%, so now you have 125 square feet is the surface area that you need for your retention-based SCMs. The PCRs does not provide any further guidance in terms of what a retention-based SCM is for the purpose of this method of compliance, technical infeasibility. So this is, up to interpretation, everybody's favorite engineering judgment. Really, you just need to do what you can in those areas to retain some amount of water, right? It could be any type of landscaping, so long as you're retaining some amount of volume before it overflows to a storm drain, right? You could have a planter box with a curve around it and your inlet is raised 3 inches, 2 or 3 inches off the ground, right? That could be a retention-based SCM. It could be a rain garden, right, which is generally just depicted as a lower lying area, and we're talking maybe 2 or 3 inches of ponding before something would overflow to the surface. It could be a detention or retention basin that's heavily vegetated, right? It could be a bioswale. So there's any number of features that you could account for in that 10% of your retention-based SCMs. And I hope that answers the question. And I would recommend, again, going back to attachment E of the PCRs. I mean, really, once you get out of the box of working directly from the technical guide, you should be referring to the PCRs. It's good practice to at least know what's in the actual text of the regulation as you're working through these requirements. I think the technical guide does a good job of bringing forth what you need to know, and certainly maybe all that you might need to know for a less complex project. But as soon as you get out of that box of, yes, I can comply with bioretention or some other standard feature, go back to the guide and read it.
For the bioretention examples, how does the calculator differ without an orifice versus with? What is the difference in volume that is considered in each case?
Okay, good question. So the calculator, it is not first I'll say that it's not a black box, right? So within the calculator, there's certain cells that you can and cannot edit, but you can go back to the different tabs and see for yourself all the calculations that it's doing. So what the calculator is assuming is, as soon as you check that box that says that yes, you have an orifice, the calculator is assuming that you have a 2-foot standard depth of bioretention soil media, because that's what's specified in the technical guide. And then you enter what your available ponding depth would be, and that would be how much water can be standing in your bioretention media before it enters some kind of inlet to your storm drain system. So oftentimes that's 6 inches. So let's say you enter, yes, I have an orifice, I have 6 inches of ponding. As the calculator is then routing your runoff through your facility, it's assuming that you have that available storage, and it's routing it as if you have a detention basin. Again, detention meaning that it's slowly allowing that water to release over time. The methods of releasing that water are primarily infiltration through your facility. And so it's doing two things. It's giving you credit for that volume, and it's also increasing that surface area that's available for your exfiltration, right? Your water leaving into the soil profile. And it will automatically, once you hit the button that says launch model, it will calculate the volume of gravel. That is the result of the calculator, is what's the volume of gravel I need in my bioretention facility, right? Your 2 foot of bioretention media is standard. Your ponding is how you've designed it. And it's telling you how much gravel you need to meet the on-site retention requirement. And that volume of gravel will be less if you choose to use an orifice because of your ability to now store more water above your underdrain.
Okay. Can you share your experiences or challenges with proprietary high-volume tree wells or planters vault systems that are used for PR2 water quality? An example would be Contact Products. They're looking at these systems for areas that have limited space to meet the PR2 requirements.
Yeah, and I will say that my personal experience is fairly limited. That we have used these tree box type filters primarily in roadway projects, especially roadway widening projects. These to me have been the most challenging types of projects because you're working within a defined right of way, and oftentimes when you're expanding your pavement or you're adding a sidewalk, now you're paving to your right of way limits. And so in those cases, sometimes you really don't have much option other than something like a tree box filter. My personal experience with the tree box filters is that the manufacturers try to make it really easy for you. You will need to be working closely with those manufacturers in terms of confirming that you are within their allowable design guidelines. Right, you will be providing them the surface area and the type of surfaces and your design flow rate that's flowing to these tree box filters, so that they can confirm that, yes, certainly you're within our guidelines, but then they really help you in terms of the available sizes, how to connect those to your storm drain system. They try to make that part easy because they want you to buy their product. In our experience, where you have a limited footprint, it's been a viable solution, and it's been sometimes one of the only solutions available. That being said, they do require specific operations and maintenance. They are now likely within the public right-of-way, so your permitting agency would certainly need to approve those upfront if you were counting on that for some type of compliance related to a private development project.
Another question that came in: can rainwater catchment that is harvested for use during the non-precipitation season get credit in stormwater drainage design?
Yes, absolutely. So your rainwater harvesting is specifically described in the PCRs as an allowable method of compliance. Generally, for any project other than a single-family home, we haven't really seen it used specifically for compliance unless the property owner has some underlying reason why they really want to capture that water. In particular, in our climate where we get all of our rain, during a short season, and then we use it during the summer, that volume, I would say, just has limited capability for meeting the PCRs. You can use rainwater catchment to meet PR1, definitely. That's on the checklist of your site design features. If you use rainwater catchment, you've met the intent of PR1. In terms of calculating a volume for your retention, I have never seen it used to fully meet the retention requirements. So that's a good question, because if your intent is to hold that water until the rain season is over, inherently you're not going to have that volume available for subsequent storm events. So in that regard, I think that you would need to do more of a water balance through the rainfall year to show how much you're using, how much you're capturing, and how that would then correlate back to the 95th percentile retention. So a little bit more time spent on the applicant side to demonstrate how you are achieving some or all of that 95th percentile retention.
Okay, the next question we received, for projects with extremely poor infiltration that can't meet drawdown, would you recommend a factor of safety, say 2.0, for the below ground gravel volume to allow for back-to-back storms? And for these projects, the gravel can be oversized to allow the 48-hour drawdown, but the gravel will take a long time to drain.
Can you repeat, please, Jeff, just the very first part of that question?
Sure. So for projects with extremely poor infiltration that can't meet drawdown, would you recommend a factor of safety for the below ground gravel volume to allow for back-to-back storms?
Okay. Yeah, and I think that we have touched on this, that the PCRs do have a factor that is required if you cannot meet that 48 hours. Then you do need to apply the additional 1.2 factor to increase your volume of gravel. So that is the answer to comply with the PCRs, and that 1.2 was developed just based on a study of you know, how often rainfall occurs in our region, statistical analysis, some other resources. And so I think that 1.2 covers your facility. You know, if you are in a situation where you're concerned about water ponding, or you have some other factors of not wanting ponded water because you're close to a foundation or you're close to a silt face, or you have other factors that would lead you to be concerned about ponded water, then certainly you would consider some additional safety factors. But if you're just strictly talking about compliance with the PCRs, that's where you would use the 1.2.
Great. There's a couple of specific questions regarding some of your examples. So for the DMA example, where you connected bioretention areas, was the additional pipe volume the only factor that affected retention requirements?
So I hope that I'm interpreting this question correctly. In that project example, we had, you know, after the developer came and said, this is where we need our parking lot in our building, we had these different discrete areas, and I can just bring up that slide, that were available for LID facilities, and that's what's shown in light green here. Those LID facilities were designed individually to manage these various DMAs. So DMA 3 drains to LID basin 3. We met the retention requirement in that individual basin. For flood control in particular, these basins by themselves sometimes were not really the right shape or size for that DMA, and that's where we used the storm drain to connect the basins to add more flexibility, to have a single discharge point from the project site, and also to allow these basins to interact with each other for ponding for the 2 through 10 year storms. You know, the ponding, any surface ponding in those LID basins was below the invert of those pipes where they were interconnected. So PR3 was met in each individual location. For PR4, the 2 through 10 year storm, we allowed those basins to basically function as a larger facility, and we had the benefit of being able to take credit for the volume stored within our pipe system. I mean, that was part of our detention volume, was the storm drain system itself.
Okay, we've got a question regarding slide 18. And that was whether the perforated bottom there was for outlet flow control.
So the perforated pipe itself is the under drain system. So it's the same concept as this detail. This detail just shows it in a schematic format. So where you see the dashed line here in this detail, this is also a perforated pipe. And so the purpose of the perforated pipe is to capture water that would exceed the available volume within your gravel layer. So this is all the gravel layer. So once your gravel layer is filled up, now, let's say in a larger storm, you need that water to go somewhere. It's routed through your under drain and now to your storm drain system. So it's the same concept here, that the under drain captures any runoff that is basically overwhelming this facility, right? In a 95th percentile storm, you would expect, because it's designed to retain, that you may fill up to, say, this level here, and you would never overflow. So in that case, the under drain in the 95th percentile storm really wouldn't be a functional component. It's in those larger storms where your facility is filling up that water is now being routed through your under drain and through your outlet, or in this case, through your under drain and then through your orifice.
And then we had a clarification. So he was referring to the perforations in the bottom of the DI, number 203.
Oh, got it.
Sorry.
Okay. Yeah. And yes, and you know, again, I'll say that this is not one of my favorite LED details, but it's a detail that I had available to really demonstrate this standpipe. But yes, the purpose of these perforations is to prevent standing water in your DI, and I have spec'd those out as well. If you have, you know, I've also seen that this is an opportunity where if you're really site constrained, you can allow for more infiltration to occur here through your DI as well. So as an example, we have spec'd out an open bottom DI that allows for infiltration. So really that, what you're seeing there would just be a measure to try to prevent nuisance water from building up in your DI.
Thank you for that clarification. Does the reduced impervious area credit only apply to determining net impervious area in the PCR category? Or do we also subtract it when determining retention tributary area for retention volume classic calculations?
Yeah, that's also a really good clarification. So and let's go all the way back to the very beginning. Let's see. So this table will hopefully help answer that question, that net impervious area applies only for water quality treatment. So in your calculation of the tier that your project is in is where you use net impervious area. You also use net impervious area to calculate your tier for retention if you are under the category of one single family home. So the net impervious is used to calculate your tier only. Once you identify what tier you are in, you use the total of your new and replaced impervious surface to calculate your treatment requirement or your retention requirement. Now, to make it even more complex, when we are talking about the replaced impervious surface, right, that's a separate multiplier. That's the 0.5 multiplier that we talked about that is accounted for in the calculator when you designate a surface as replaced. So to try to summarize, net applies to your tier designation. It does not apply to how you calculate your tributary area or your water quality flow rate.
Great. We got a lot of very positive comments about the presentation, so thank you all for those positive comments. What is your understanding of the minimum separation requirements from underground SCMs to estimated highest level of groundwater?
Yeah. The most common requirement that I have seen is 10-foot separation. And I really appreciate in that question that you described it as high seasonal groundwater. So it is important to really understand the difference in potential groundwater between your dry season and your rain season. If you have a site where you anticipate you may be close or have groundwater close to the surface, you really should be checking that groundwater during the rain season and close to the end of the rain season when it might be its highest. And generally the criteria is 10-foot separation, and where you need to confirm that is with your county health department. So your county health department will generally have separation criteria from any type of infiltration facility and groundwater.
There was a further question regarding the seasonal changes in groundwater with regards to percolation testing. Is there some type of control or adjustment based on the seasonal changes?
So there is no real adjustment, but what's done in a standard procedure for percolation type testing is that you first saturate the soil. So in general, you should always be testing under saturated conditions, meaning that your soil is at its full holding capacity. It doesn't represent standing water per se, but it will be a lower rate than if your soil was dry. So the factor there is that you should always be testing under saturated soil conditions. In that case, so long as you have that 10-foot or more separation, the groundwater itself shouldn't really be affecting the movement of water once you are saturated.
Then we had a comment. Did you want to bring up that the underground chambers are considered EPA Class 5 injection wells and require registration?
Oh, thank you. Yes, that is a really good comment. So, and it is just as that comment stated, that underground infiltration is considered an injection well and does need to be registered with the EPA. The only exception that I'm aware of is an underground chamber, and this includes dry wells as well. So a dry well and underground chamber for any project other than one single family home needs to be registered with the EPA. If you are a single family home with a dry well on your property, then it is considered a minimal risk and therefore not required to be classified. There may be if you are in the condition where you're registering with the EPA, it's definitely worth checking in with the regional board to confirm that based on your site-specific criteria, you know, where you're located relative to groundwater or otherwise, that you don't have any additional conditions on top of that.
Is it critical to always place BSM and rock under the slope sides of a bioretention basin if these sides aren't considered part of the infiltration area or included in the basin volume calculations?
Yeah, so let's look at that detail again, and let's see, we're getting close. And again, this is the detail that I wouldn't necessarily use for construction, but I wanted to use it for discussion. So this detail shows the BSM extending up the slope. I would recommend not doing this for two reasons, right? Because as the question stated, we're only accounting for this flat area that fills up like a bathtub for our infiltration, for our effective infiltration area. This is where you're really taking credit for that bioretention media. So why bring in this expensive material if you don't need it for compliance? And the bigger issue that I see with the way that this is drawn here is that this material is much more highly susceptible to erosion than a typical native soil. So here again, if you did have bioretention media extending up a slope, anywhere where you have concentrated flows or suspect that flows are going to be coming into your facility, you should be protecting from erosion, right? You should have rock here to protect from eroding this portion of the slope. My preference would be to extend this native soil all the way down to the base of the bioretention facility, because in general, native soil is going to be more stable, more compactable than a bioretention media. So that can help minimize that erosion. You know, there may be some need for the health of your plants to incorporate some compost or do something else here to the native soil to promote the vegetation growth in your facility, but I would recommend that is not BSM. Whether or not you extend the gravel beyond that is really dependent on your site constraints. If you have a site where you're really constrained at the surface and you need more subsurface storage, certainly you can extend the footprint of your gravel beyond that bioretention media. But again, that just requires that now your total excavation area is larger. So it's just a balance of cost and site constraints.
Well, we are at 11:30, so I just want to say thank you to everyone for participating today. Hopefully we got to the majority of the questions. I apologize if we didn't get to all of them. But you can feel free to shoot us an email via our website, montereyc.org, SEA, for further questions. Valerie, I just want to, again, thank you. Great job today. And thank you to everyone.
Yeah, and then just to add to that, Jeff, again, my contact information is here on the closing slide. And I believe, Jeff, that you were planning to provide this as a PDF as well. I know we were going to give that to you as a PDF. If anybody wanted to go back and actually reference the slides, and please reach out with any questions you may have, something that we didn't get to answer today through Q&A. And I appreciate you all attending and listening in for this long duration training.
Yes, I'll forward the presentation to all of the registered participants. So,
great.
Thank you, everyone. Have a great day.